Greetings. All right. All right, I want to start off and show you just something cool. Um, yesterday, yesterday you found the derivative of sine and cosine, and I kind of gave you a few different ways to look at it that were kind of neat. But I want to do just one other way, not so much to like you don't already know. We now know the derivative of sine is cosine. The derivative of cosine is negative sine. But let's just take a look. Yeah, well, the old way. I skipped a whole bunch of stuff in chapter 2 about limits, and that's just because it's introduced to you in a place where you're not in a position to kind of understand why it's kind of cool. And here's a place where we would be benefiting from that. And so how about if I just show it to you now in context, and then it'll maybe make a little more sense. So let's say that we are looking at the cosine of x, and we're wondering what its derivative is. Well, remember the definition of a derivative is that f prime is equal to the expression with x plus h plugged in minus the expression itself, all divided by h as h goes to 0. That was just the good old-fashioned slope. Remember, what used to be down there was x plus h minus h, and we just noticed that, I'm sorry, x plus h minus x. And we notice that the x is canceled out. But that's the classic definition of slope. It's y minus y over x minus x. And so, you know, what would that look like here? Well, I guess it would look like, well, x plus h plugged into that. I guess that'd be the cosine of x plus h. And then minus f of x, I guess that'd be the cosine of x, all divided by h as h goes to 0. Like that's the classic definition of slope. And we've kind of, you know, started moving into shortcuts to this and so forth, but it's like I can't put h of 0 in now, as we decided before. And this is kind of even worse than we did this with square roots, and we saw if we multiplied by the conjugate that we could get the h's to cancel, that h on the bottom could go away. We saw that if we had a couple of fractions, fraction minus fraction, we could multiply the top and the bottom by things that would make the h go away. But what would that look like here? Well, if you stare at this, you should sort of think, I don't really know what I could do with this. There's multiplying by the conjugate actually doesn't help. I can't seem to simplify anything. I'm just staring at it. Well, the only progress you might make with this, if you look at my trig sheet or go back in your mind's eye, is there was a way to expand cosine of junk plus junk. And I don't remember what that is off the top of my head, but I'm looking at my note sheet now too. There's an identity about this. I'm looking at that sheet, and it says that if you have the cosine of junk plus junk, my note sheet says x plus y, that would expand to, and this is all I would hope from Math 112, is that when you see that, you'd say, hey, there was an identity about that. That could be rewritten. Cosine of junk plus junk is the same as the cosine of the first one times the cosine of the second one minus the sine of the first one times the sine of the second one. And again, I wonder, could you make that for yourself? Like there's a little identity. Can you build that for yourself? Do you understand where that came from? Can you make that? I hope your teacher showed you how to make that back in the day, so that you could get this back if you wanted to, if you're just curious, like where does that come from? So let's see, what would that mean to us then if we sort of get back to our answer? Well, cosine of x plus h. Well, then that'd be the cosine of x times the cosine of our second one is called h, not y, minus the sine of x times the sine of h. So there's cosine of x plus h expanded, and then there's still that minus cosine of x sitting there, and it's all over the top of h. So you should say, hey, that doesn't help. Like what good is that? It's just worse. Like it's just kind of a big mess. And so what is that equal to, or where can you go with this? Well, again, it just takes a little bit of creativity to even notice this, but at least you could say, hey, this term and that term have a cosine of x in common. So let me write out what that would be. I could factor the cosine of x out of both of those, and let's see, what would that leave behind? It would leave a cosine of h behind. And then as a placeholder for the minus cosine, it would be minus 1 all over the top of h. Do you agree with that? Notice everything up here, all three terms are divided by h, and so I sort of just took those first two terms, and now I'm going to just look at this second one, this term right here, and say, well, I guess that could be minus the sine of x, and then what's left is the sine of h over h. Now, the only reason I'm separating out the x's from the h's is, remember that what we're trying to do here is let h go to 0. And we always wanted to just let h be 0, but notice we can't do that yet. You notice the h doesn't cancel out. Like this h is still here, so you can't put h as 0 in there. And the same thing is true with the green one over on the right. Like there's still an h, like we can't do it. That doesn't do any good, really. But this is why chapter 2, or why the concept of a limit is cool. So although h cannot be 0, h isn't 0, we can look separately. And I'd like you to do this on your calculator. You can look separately at what happens to cosine of h minus 1 over h. What happens to that as h gets really close to 0? This is what chapter 2 spent a lot of time with. So if I bust my calculator out, now there's nothing algebraic you can do with this. You actually got to have some skills you don't have yet to answer this question algebraically, but I'm just going to get my calculator out and type cosine of, well, let's try 0.01. So I'm going to let h be 0.01, and let's see what that limit is equal to, or what it's approaching. So I say cosine of 0.01 minus 1, and I have to divide all of that by h. So you got to put parentheses around in your calculator. You've got to add an extra set of parentheses here, otherwise the whole thing won't be divided by h. So I'm going back and inserting that parenthesis right now. So I say divided by 0.01. You should be doing this with me. And I got negative 0.004999, like 005. And so now I'm going to try 0.001. Like this is what it means to approach a limit. I can't let it be 0, but I can let it approach 0. So if I go back and put in 0.001, I got this time negative 0.0005. And so I don't know about you, but it sort of seems like this is on its way to 0. Notice it doesn't break. If you put h as 0 in, you know what happens here. If I put 0 in, cosine of 0 is 1, then you got 1 minus 1 over 0, you got 0 over 0, it breaks, it explodes, it doesn't work. Yet, if you let it approach 0, it doesn't break, and it actually, the limit of it is 0. So that means this whole thing just goes to 0, and 0 times cosine, that goes away. What about the second one? What about this one here? What about that one? What's the limit as h goes to 0 of the sine of h over h? What happens to that one? Again, I'm going to cut to the chase this time, and instead of trying 0.01 first, I'm going to go all the way to 0.0001. Like, why try something not close? Let's just try something close from the start. So I say, what's the sine of 0.0001? divided by 0.0001. And I got 0.999999, the whole bunch of nines. And so it appears that this is on its way to 1. So there is nothing algebraic we can do to actually plug in h as 0, but this is why chapter 2 is a thing. Like just the fact that just because you can't plug h as 0 in doesn't mean this isn't approaching a limit. So if this approaches 1, then why are you not surprised? Why are you not surprised given that we were trying to find the derivative? What is all that equal to? Well, since cosine of x times 0 is nothing, and negative sine of x times 1 is negative sine of x, isn't that another reason why? Remember the original problem was f of x equals cosine of x, and we were saying, what's the derivative of that? Well, the derivative is negative sine. Isn't that what we found yesterday? We found the derivative of cosine was negative sine. And so it's limits, it's limits that allow us to kind of answer that question. We saw it graphically yesterday. We saw that, hey, it looks like sine, but flipped upside down. That was cool. But this is kind of another, well, kind of a proof of it. And it also is allowing me to sort of make sure you understand the intuition behind a limit in chapter 2. We skipped a whole bunch of sections, but it's because of this. Like this is why a limit exists and why it's kind of cool. So slope is always f of x plus h minus f of x over h. That's what slope is. It's y minus y over x minus x, and we just let h go to 0. That's true every time. It's just that you can't always get yourself out of that mess and get the h's to cancel. You can't get the h to cancel here. Yet that doesn't mean this doesn't still approach a limit. So that's just kind of cool. Just interesting to note. Don't need to know that, but it's just kind of cool. What I'd like to do now is go on, and I'm going to have you go into breakout rooms to figure this out. But what about a function that's tangent of x? How are we going to find that? Now, let me just give you let's just think about this for a second. Well, one answer that is painful and unnecessary is to say, well, what we just said a second ago, which is that would be f of x plus h minus f of x over h, again, as h goes to 0. And we could kind of play around with that. And this would work, by the way. This would work because we have an expansion for the tangent of two angles added together, and we could play with the limit. But we have a better way to do this. We have a better way. And that is, isn't tangent, you should know this from trig, how can I rewrite tangent?
Sine over cosine.
Sine over cosine.
Tangent sine over cosine. In other words, all the other trig functions are made of sines and cosines. You can't take the derivative of tangent, but can you take the derivative of sine over cosine? What should you be thinking if you take the derivative of something that says junk over junk? Which one of our rules governs what?
Quotient rule.
Quotient rule. What I'm going to do then is disappear all of you into a breakout room with 4 other people or so. Actually, maybe like 3 other people or so. And I want you to collectively, between the 3 of you, try to take the derivative of tangent by thinking of it as sine over cosine. You know the quotient rule. Look it up on my note sheet. You know the derivative of sine and you know the derivative of cosine. So could you build the formula yourself? And the answer is you definitely can. And you have the right answer to this on my note sheet. So check it against that. But I want you to talk it over with other people. Maybe one of you will be the quickest or smartest at it, but just kind of make sure that before you leave that, everybody in there kind of gets that. And if you have time, I'm going to sort of call you away from that maybe before you're done. But if you have time, go on and try not just tangent, but try one of the other weird ones like secant. Secant can also be rewritten as something, and it also would involve the quotient rule. So I'm going to create some breakout rooms right now. Let's see, how many of you are there? I see there are 19 of you, so 3 would be 6. I'm going to create 6 breakout rooms. And I'm just going to give you some time in there, and then I'll just call you back out of there. So you are now invited to random breakout rooms. Turn your video on when you get in there just to get to know some people a little bit. Jake, you and Julian feel like you're making any progress with this? Feel like something good is happening? You're on mute, Jake.
Yeah, just setting it up so it's like instead of tangent, it's like sine over cosine.
Sweet. Do you feel like you got the quotient rule concept that you're sitting there with the derivative of the top times the bottom left alone minus the derivative of the bottom times the top left alone? Does that feel like it's working for you?
Yeah, and I compared to yesterday, right? It pretty much applies the same stuff.
Yeah. Sweet. Good. Carry on.
Thank you.
Are you guys tracking? Any good things happening?
Yeah, I tried doing it, but I think I was close, but I messed up on one thing, so I'm trying to retrace what I did wrong.
Sweet. Are you not getting it to agree with the note sheet, so to speak?
Yeah, I'm getting like secant squared x instead of secant 2x. So
No,
I'm not.
you should get secant squared. That's a squared, not a. You should get secant squared.
Oh, I should? Okay.
Yeah, if you got secant.
Oh, sorry. I thought it was like a 2x instead of a squared x.
No, it sounds like you got it to me.
Okay, yeah, I think I figured out how to do it then.
Sweet, good job. I'll give you guys a little more time. I'm going to call you back to the other room in just a minute.
Sure.
Cool.
You're muted.
Thanks. I didn't say anything yet, but I was about to.
Yeah, I wasn't sure. It looked like you were getting ready or something. So
Thanks for saving me. So yeah, I mean, I hope that was profitable. I hope you find yourself looking at that going, wow, I can make these for myself. I'm gonna quickly do a different one. Let's say like one maybe you didn't do, cotangent of x. So, and this is also just good review for, the tools we have now. So it's cool to make this stuff for yourself. This is not hard, but you of course do have to speak the language of algebra to pull it off. And I just kind of want to warn you, I've been kind of talking about this way, but it's like, if you're going to go to Madrid, Spain, it'd be awesome if you could learn Spanish before you went, because you're going to just be able to get a lot more stuff done there in that town and enjoy it a lot more if you can speak the language. And that's true here. Like if you don't speak the language of algebra, the trigonometry, you're going to have a hard time getting stuff done in this language. And I just want you to notice, like, my problem here is not calculus, it's algebra, and then, do something about it. But since cotangent, for instance, it can be rewritten as cosine of x over sine of x. And then the quotient rule says u prime v minus u v prime over v squared, where the top was kind of the u and the bottom was the v. Then let's see if we can figure out what the derivative of cotangent would be. So u prime, derivative of cosine, we just reminded ourselves a second ago, was negative sine. And then times v left alone, times the sine left alone, and then it's always a minus sign. And then u gets left alone, the cosine gets left alone, and then times the derivative of the bottom. The derivative of sine, we said, was cosine. And that's all over v squared, the bottom one squared, all over sine squared. And so cool. Let's see. And I guess I want you to understand, do you understand? Because this is kind of problematic today. Like, you're done right now. You're done. That's the derivative. You're done. Calculus is over.
That's a little complex to read, though.
Yeah, like, but you're gonna have to use this. Like the whole, you only do that. You only stop here if you're just gonna find the derivative and you're done. But remember, we're using this to find the slope of a curve, and so I'm gonna have to plug in, x is 2 or x is 6 or x is 96 degrees or whatever. And so I don't want to. If I can make that any easier on myself, I certainly would like to. And so the point is calculus is over. But the question is, can you clean this mess up a little bit? Can you do something to make your life a little better? Well, I have negative sine times sine. That's kind of nice, because now sine times sine, there's only one x there. That's kind of nice. And then cosine times cosine. And so that's a little bit better. Hopefully you speak the language of algebra well enough that your next move is not to go, yeah, I'm going to get rid of those. You are a violator of the distributive law if you think that is okay. It is not okay. However, that's better. But there's even something else that's awesome here. Maybe you saw this when you were doing tangent, but anytime you see sine squareds and cosine squareds, you should be thinking, hey, there was that identity, sine squared plus cosine squared equals 1, but it's not quite right in this case. Did you notice in the problem that you did that if you took -1 out of both of those, distributed out instead of in, that, yeah, now we're talking. Now, because that is sine squared plus cosine squared, I can replace that whole thing with 1. And so, sweet. So you might say -1 over sine squared x. That's better. That's better than what we had back up here. Much nicer than this. Now, I would argue that's probably the best answer to this question.
Are there still going to be times where that, I'm sorry to interrupt, I was trying to raise my hand, but are there still going to be times where that will be undefined though?
Yeah, in other words, are there angles where the sine is 0 and then 1 over 0 is undefined? It's a brilliant observation, Jake. So let's see, when is the sine 0? The sine is 0 since sine is the y coordinate, like at pi. So if I said the slope of cotangent back here, and I was interested in when x is equal to pi, then when I go down here, the sine of pi is 0, so you get undefined. Well, what does that tell you about the original cotangent graph? Well, it tells you that it's infinitely steep there. So yeah, that actually, there is times, and that actually tells you something about the graph. So that's an excellent observation. And I would actually invite all of you, if I'm not looking up, please interrupt. Don't apologize. Like, I want this to be a conversation. I want you to ask those questions. You all just learned something because Jake asked a good question. So that's oftentimes better than just hearing me ramble. You should also know that
So
1
just to
over
clarify, I'm
cosecant.
sorry.
Yeah, go ahead.
I think that with this compared to what we were doing like towards the end of last week and the beginning of this week, it's like we're not getting to a point where it is, or because before we were getting to a point where we could just put 0 in, where sine squared x would equal 0 and it would still work, where we were trying to get it so it wasn't alone on the bottom.
Yeah.
But we aren't trying to get to a point on that. It's more like the beginning of the term where we're just trying to establish a place where we can guess and check.
Yeah, the reality is as x gets really close to pi, or as x gets really close to 0, this slope is going to get huge. So in a sense, at x is either pi or x equals 0, the slope of this is undefined, but a better way to think of that is infinity. If you just let x approach 0 instead of let it be 0, -1 over a number really close to 0 is going to be a huge number. -1 over 0.001 is something like 1,000. So now you have a slope of -1,000. Well, let's take a second and go look at the graph of, cotangent, since that's the one we're looking at. And this is another advantage to Desmos. It actually has all the trig functions. Your calculator only has 3 of them, but this one has them all. Well, what do you notice about this graph and I'll even graph this in here, as x gets close to pi? Do you see how that purple graph of cotangent has an infinitely tall slope? Like, that's exactly what it's saying. And so in a sense, the fact that 1 over sine squared can have a place that's undefined, a better way to think of undefined is infinity. Yeah, right around pi, the slope of that purple graph actually is infinity. It's infinitely tall. And that happens again at 0 and all the other places where sine is equal to 0. And so in a sense, it told us something about the graph that we might not have known. Like you probably didn't study the graph of cotangent very much. I hope you didn't. So that is a very interesting point. Does it make sense that somebody could choose, since 1 over sine is equal to cosecant, somebody could choose to rewrite this like this? I would say both of these are good answers. You'll notice on my note sheet, I said negative cosecant, and I only did that because that's what's in the book. I personally actually prefer this answer better. And the only reason I say that is because I'm about to use this. Like, let's say I'm interested in, since y was equal to the cotangent of x, I am interested in the slope of that at angle 1, like 1 degree, or not 1 degree, 1 radian. I want to know what the slope of that cotangent curve is at 1. Well, does it make sense? I don't have a cosecant button on my calculator. So even if I wrote down the derivative of cotangent is cosecant squared, I'm still going to have to be using this one. Does that make sense? So let's see, I'm going to type that in my calculator really quick and just kind of check my work. Let's see. So -1 divided by the sine of 1. So I'm taking -1 divided by the sine of 1 squared. Now I think you can actually be lazy in your graphing calculator. I think you can actually type the sine of 1 and say squared after it. And it knows to square the whole thing, not just the 1. So I got -1.4 for the slope of the cotangent curve. Well, let's go over and look at the graph just because it's fun. If you went to 1, let's go to the point 1. I'm going to graph it just so you can look at it. 1, and then to get y, I have to take the cotangent of 1. So rather than figure out what that is, I'm just going to let Desmos do it for me. So there's the point. Does that point look to have a slope of -1.4? Well, at least the negative is right. How could I cheat and actually see what the slope is? Well, you can't.
Could you just type in f prime of x? Oh, like change it to f of x and then type in f prime of x?
Exactly right. And I want you to be checking your work. That's why I keep showing you this stuff. And why I've said this before, and Jake is correctly remembering. So it does understand f prime. So if I rename that f and then I say, okay, I'd like f prime of, and I can't say x, but I can say f prime of 1. Notice, okay, cool. It's like, this is working. Do you see what I'm saying? Like, don't forget, we're doing something real. We're doing something tangible in the world. We're taking the derivative of cosine. We're finding a recipe to tell us the slope of the cotangent graph. That's what a derivative is. Keep repeating that because I want to make sure you don't miss it. It's a recipe to find the slope. And apparently the recipe that you just made in the breakout room is actually working. Well, hopefully you made it. So I write that down. Like, I don't want to do that again. I made it once. I now know what the slope of cotangent is. It's negative cosecant squared, or negative 1 over sine squared. And so I'm going to write that down. That's why it's in your note sheet. I don't want to make this ever again. Let's do let's make one more of them. You should go make them all, but I'm going to just make one more of them for you. Let's say the original graph is 1 over cosecant. And you want to know, what am I doing? That's not true. It's not 1 over cosecant, it's cosecant. I want to know, what is the slope formula for, say, cosecant? And I have no idea what to do, except for the fact that I can rewrite it as 1 over sine. And I know the derivative of sine, so now I can do it. But this is the quotient rule. Now you may argue I can move it to the top of the negative sign. That's true, but you don't want to do that right now. Just take my word for it. I'm just going to use the quotient rule. It's sitting there. This is my u, this is my v. So the quotient rule would say that f prime of x is equal to the derivative of u. Hey, that's cool. The derivative of u is 0 times v left alone minus 1 left alone times the derivative of sine, which is cosine, all over v squared. So this whole term goes away, and the top is just negative cosine. So I get negative cosine over sine squared. Again, that wasn't near as much work, but I'd say that's a good answer. You're done. There's nothing wrong with that answer. That's not what's on my sheet, but that's a good answer. If I was gonna like find the slope when x is 1, that seems like not terribly hard to plug in. But do we have some other ways to write that? And this is the part about
Negative
speaking the language of trig. What could I do to this? What could I do to this to rewrite it, or to get it to look like what's on my sheet? And again, I don't that doesn't make what's on my sheet or what's in your math book better.
So we have a cosine over sine there, which is cotangent, and then we have a 1 over sine there, which is a cosecant. Cosecant. So that's negative cotangent times cosecant, right?
Yeah, Vail's on it. If I think of that as a fraction multiplication problem where it's all been multiplied together, now I'm just going to move it back apart. There's a cosine over a sine. Cosine over sine is cotangent, and then 1 over sine is cosecant. So there's another answer to this. Now, why do you think this is what's written in your math book and what's written on my note sheet? Why would you choose that one?
I mean, it's sort of fascinating how, all the different trig functions happen to relate to each other in this way, I suppose.
Super neat. Yeah. And I like to think of it as kind of like, you and a blade of grass are made of carbon, hydrogen, and oxygen. It's like the same ingredients, the same Legos, and yet you can build totally different things. It's just really cool. It's a cool way to look at it.
Is it because that's it in its simplest form? Like, you can't simplify it anymore from there?
Yeah, that's kind of true. It seems like math books prefer to just write it not as a fraction. It's like, hey, the fraction's gone. I mean, I don't like fractions. I get that. But I think this one's better just because I don't have a cotangent or a cosecant button on my calculator. So if I'm going to actually use this to find the slope when x is 1, I'm actually going to have to kind of go back to that to be able to do it. Does that make sense? If we had all 6 trig functions on our calculator, then I would agree that cosecant cotangent answer is probably the best one. But my point is that's debatable. Go ahead, Felix.
Oh, I was just going to say it depends on whether you view the purpose of it as a usability versus, nice looking formulas.
Yeah, exactly right. So make all of these, and maybe you even come up with an answer you think is better. But sines and cosines are nice. I mean, keep in mind the other thing is what if I asked you for f prime of, say, pi over 3? Like, in other words, instead of just picking a random number like 1, what if I said, hey, let's go find the slope of that curve? Remember the original graph, I've forgotten already, was cosecant. So we're saying, hey, cosecant graph. I forgot what that looks like. We'll go look at it in a second. But I want to know what the slope of that curve is at pi over 3. Pi over 3 might stand out to you from the unit circle as one of those exact ones. Like, there's actually an exact slope for this. So let's just play around with that for a second. So if I go back over here, and by the way, you don't have to go to that function button. You can just type it, CSC. It knows that you mean cosecant for that. You don't actually have to go over to that function button. And we're going to figure this out. We want to know what the slope is at pi over 3. So first of all, just look at the graph. Hey, look, looks like a bunch of parabolas. They're not quite parabolas, but looks like a bunch of parabolas. And I'm interested in what happens at pi over 3. So I'm going to go in here and type that. Let's see. I can't remember where pi is. I know there's a place for it. I think you can type pi, but no, there it is. Pi. I found it. Divided by 3. And then we're using cotangent. But now that I have called it f of x, I can just replace. I don't even have to write cosecant. I can just say f of pi over 3, right? F of pi divided by 3, close the parenthesis, go to the right, close the parenthesis, close the parenthesis. So there I am on the curve. And so notice you now say, hey, look, it's apparently negative. I didn't know that before. And notice we know the answer. If I go back and cheat here and type pi divided by 3. Where did my stuff go? Pi divided by 3. Notice you recognize it probably. We get a recognizable decimal here. Doesn't look like negative 2/3. You're sort of lucky that that decimal was recognizable. It appears that the slope is negative 2/3. The purple graph would indicate, yeah, that slope would be negative, and negative 2/3 looks about right. But let's just see if we can do this kind of the way my open math might want to ask it. Like if we had to actually find the slope of that point and get it perfect. Again, you get lucky here if you recognize that's negative 2/3. You type negative 2/3, great, you're done. You just sort of cheated and got it right. But let's see if we can do it back this way. Well, wouldn't the answer to this be the cosine of pi over 3 divided by the sine of pi over 3? And whatever answer I get for that, I'm going to square it. But now look at your trig. Look at your unit circle. Remember, the cosine was the x coordinate of pi over 3. And the sine is the y coordinate at pi over 3. I'm going to look at mine, but I'm not going to unshare my screen to get it. But if I'm at pi over 3, the x coordinate is a half. Cosine of pi over 3, the x coordinate of pi over 3 is a half. The y coordinate is the square root of 3 over 2. Is that what you're seeing? Like that's why I like the cosine and sine answer, because I can steal those off the unit circle. Had it been cotangent and cosecant, I would have had to think a little bit more. Well, let's see, what is that equal to then? I got negative, I still have a half, but what's on the bottom? Square root of 3 squared is 3. 2 squared is 4. So now I have negative 1/2 over 3/4. Well, that'd be negative 1/2 times 4 over 3. So I got 4/6, or I could cancel that to 2 and that to 1. Look at that. That's exactly what I thought. I get negative 2 over 3. And so you can get it. This is the kind of question you would see in a math book. Again, I prefer to use any angle, not just the exact ones. But you got to be able to speak the language of trig to be able to get stuff done in this land. Otherwise, you're kind of in trouble. And again, what I want you to notice is the calculus of this wasn't terrible. Like if you know the quotient rule, we were done with calculus pretty quickly. But it's like, can you still move stuff around in trig? I mean, that's what's cool about trig. Any thoughts on that? So my advice to you would be go. I just did 2 of them, but don't look at my notes. Go rebuild them all for yourself. Be able to make these for yourself. The confidence that gives you as a mathematician that I don't need someone to tell me. I don't need someone to tell me what the answer to these are. You'll survive. You can survive this class looking at my note sheet. If you need the derivative of tangent and you look at my note sheet and it says secant squared, you'll survive this class. But you're not going to speak the language. You're not going to understand it deeply. You're not going to be able to use it for anything. And that's kind of like why I started off yesterday the way I did. I gave you that problem with the tree growth and so forth as kind of a rhetorical question. Do you speak the language of algebra and calculus well enough to be able to do anything with it? So being able to build it is really important. Go build tangent. I just did secant. I'm sorry, I did cotangent and cosecant. Go build them all, but certainly the other 2. And you're more than welcome to stay after class and discuss any of these things. But what I'd like to do now is just let's use this. Now that you have in front of you the derivative of all of them on your note sheet that I gave you, let's just try to do some random problems now and just see if we can answer this. So for instance, we could do something like this. I'm going to give you a second to think about this, but if I said, all right, f of x equals, I don't know, 5 times cosine times tangent, for instance. And I asked you, what is the derivative of that? Like, could you take the derivative of that? I'll give you a second to try it. Again, what should your first thought be? What is it going to take the derivative of junk times junk? What should you be thinking?
The product rule.
Yeah, nice job. You should be thinking, hey, junk times junk. I'll do this with the product rule, and to save you a little trouble, like just have the 5 go along with one of them. Like there's your product. There's your 2 things. 5 times the cosine will be the u, and tangent of x will be the v. And then you look at my note sheet that says that the product rule is u prime v plus uv prime. Like, what do you get? And then if you have time, try to check it. Don't wait for me.
Would it be cleaner to do turn 10x into sine over cosine and use the quotient rule?
We'll talk about that. Yeah, try it just like it sits, but Caesar makes an awesome observation there, and we'll go back and talk about that in a minute. But try it just with the product rule first, and then nice job. So I'm going to catch up to you. So it doesn't take long to do the calculus. If you know the product rule, calculus is pretty quick, and I bet most of you got that part right. The question is, did it simplify, and could you survive any of that? So if you say, okay, the product rule is the derivative of u, for us, that's 5 cosine. Well, the derivative of cosine is negative sine. So you'd say, okay, that's negative 5 sine. There's u prime times d left alone, so times the tangent. And then always a plus sign for product rule. Then I get to leave 5 cosine alone. That's my u, but then I got to multiply by the derivative of tangent, v prime. Derivative of tangent, you look in your notes, is secant squared. Done. That's the answer. You're finished. But maybe it cleans up. Maybe stuff goes away. And one piece of advice I'll give you that you may have gotten in your Math 112 class is that everything is made of sines and cosines. And so maybe some stuff will cancel out if you just switch everything into sines and cosines. So change to sines and cosines. That's never a bad idea. There's all kinds of creative things you can do. Trig is really neat and complicated and so forth. But if you just switch everything to sines and cosines, oftentimes beautiful things will happen. So let's see, I got negative 5 times the sine of x, but tangent is the sine of x over the cosine of x. Notice that's not very good news. I was hoping maybe something would cancel there, but I've got sines on top and cosines on the bottom, so nothing really cancels. So maybe this isn't going to do much. And then plus 5 times the cosine of x. But then secant is 1 over cosine, so secant squared would be 1 over cosine squared. And so that's better news, because that means there's a cosine on the top and a cosine on the bottom. And so maybe something cancels there. So I could say, cool, one of these cosines cancels with one of those. And so, I don't know, let's just rewrite what we've got. You multiply fractions straight across, so I guess I'd have negative 5 sine squared on the top and a cosine on the bottom. And then I have a plus 5 on the top and a cosine on the bottom. So just a side note, but is that better? I would say it is a little better. Why is it a little better? Well, we used to have 4 x's back here, and now we only have 3. So that's a little better. But
you can also, when you add them together, you can cancel out the 5s because they have the same denominator.
Yeah, notice this is a fraction that wants to be added, and it already has a common denominator. So if I did add them, I'd have negative 5 sine squared x plus 5 over cosine of x. And so now you're down to even 2 x's, and so that's even better. Are we done?
You can divide 5 out of it, or negative 5, and turn sine x minus 1.
Yeah, I could divide a negative 5 out of it, which sort of seems like that isn't really going to do a whole lot of good. But perhaps if you did that, if you took a negative 5 out of it, you might suddenly recognize that
The sine x, or the sine x squared minus 1 is equal to cosine squared.
yeah, you might notice something that I could very easily see somebody not noticing, I guess is what I'm saying. I could see a person saying, I think I can stop right here, and I would totally get that. But in this case, if you take that minus 5 out, you might remember the identity. You might have memorized the identity that I'm going to write it in shorthand. Sine squared plus cosine squared equals 1. But that's not what this says. This says sine squared minus 1. Well, I guess I could subtract that 1 over to this side, sine squared minus 1. But then I would have to add the cosine squared to the, or subtract it to the other side. So sine squared minus 1 could be replaced with minus cosine squared. Minus 5 times minus cosine squared. Wow, that's particularly cool because a negative times a negative is a positive, and then as you probably see, this cosine cancels with one of those cosines, and so this actually just went down to 5 times the cosine. I mean, that'd be really cool if you saw that, wouldn't it? Now, on a test, how far do you have to go? As I said, would it be weird for somebody to stop here and just kind of think they were done? That's going to be kind of tough on a test. I'm going to try to give you some hints. Like I might say something like simplify it a little, or I might say this one simplifies a lot. Like don't quit because it goes a long way. I mean, I would kind of want to give you a hint. The problem on a test in this class is you could burn 30 minutes here, especially in this problem I made up very carefully so that it would work out nice. But I'm going to make some up more, a little bit more randomly in a little bit. And sometimes it's kind of hard to tell, am I done or, how do I get further? So that's a really good answer to this question. So now back to what Caesar noticed. Right at the start of this, 5 cosine of x times the tangent of x. Let's just stare at that for a second. Skip down to here. If you wrote 5 times the cosine of x and even right then switched it into sine of x, switch tangent into sine of x over cosine of x, what do you notice about that statement before you even start?
You could cancel out cosine of x.
Yeah, those cancel out. And so the original problem then is just 5 times the sine of x. What's the derivative of sine of x?
Cosine.
So you can change stuff around in trig anytime you want to. So as it turns out, if you'd noticed that simplification before you even started, this problem would have been even simpler. But you don't have to notice that to get it right. Does that make sense? There's not one way to do this. There's 20 ways to do this. If you like pain, go back and switch tangent out for the square root of secant squared minus 1 or something, and then proceed. Like you can make this worse, you can make it better. It all works, but you got to speak the language of Spanish to get stuff done in Spain. And this will tax you a bit because people typically don't leave Math 112 really all that great at this. I don't know. Let's just play some more. Let's see. Let's go back over here. I just want to like find a graph that's kind of fun. I'm thinking about like mixing. Let's see. What would it look like if we did? That's kind of fun. Let's do that one. I can appreciate somebody, looks like a tooth. I actually notice it's a lot bigger than I thought. This is sort of like a crazy vampire tooth looking graph. But again, let's do something practical and check our work. So I'm going to just take us to a point on this graph that we want to find the slope of right there. Would you agree? What do you think the slope is right there on this tooth looking graph? You should have a decent estimate in your mind. You should see that as a positive slope, but not very big. You agree with that? So this slope to me looks like 1/5 or 1/6 or some small positive decimal, 0.1, 0.096, I don't know, some 0.22, I don't know. And notice I picked an angle this time that isn't perfect. 1 is a nice angle in radians, but I'm going to have to kind of cheat to get the answer. So my question to you is, can you find the derivative of that? So example, what if f of x is equal to x squared cosine of x? A mixture of polynomials multiplied by trigonometry. You have no choice here. You can't clean this up, but to do this as a, well, again, a product rule problem. And so can you find on a test, can I ask you a question like this and say, find f prime of 1, which means not only find the derivative, but then plug 1 in. And could you even find the equation of the tangent line? You see some of this in your assignment, but I haven't done that much of it in class. So let's do that as well. And check it all. Let's go back to the graph and check and see, can we actually get all this done? Again, I'm going to give you a second to get a head start.
Do you want us to do this in tangent or in radians or degrees?
Radians. we'll just do everything in radians unless I say otherwise, or we have some kind of a project that would make more sense to do it in degrees. Shouldn't take you very long to write out the derivative of this with the product rule. I'm going to catch up to you and see before you try to simplify it if there's any simplifying to be done. But like this is a good test question right here. It's a great test question. It allows you to check your work, forces you to see if you understand what a tangent line is. So if u is x squared, the derivative of that is 2x times v left alone times the cosine of x left alone, and then there's a plus sign. And then I get to leave the x squared alone, but then I got to take the derivative of cosine, which is actually negative sign. So it would make more sense then to go back and just put the negative sign right there. That would be f prime of x. Now in this case, I think we're done. Like I don't think there's really any simplifying you could do to this. I mean, I guess I could take an x out of both of them, factor an x out, but I'm not sure that would save me any time. Again, if you want to be technical about what simplification means, it probably means, well, there's 4 x's I have to plug in to answer this. I got to put 1 in every one of those places. So if I could make it so it was only 3 of them, then I guess that would be simple. That would be a little simpler. But now we can say we know how to find f prime of 1. Well, I guess that would be 2 times 1, which is 2 times the cosine of 1. I can just type this whole thing into my calculator. Minus 1 squared times the sine of 1. I mean, type the whole thing in. I'm going to type in, just because I'm not totally lazy, I'm going to type in 2 times the cosine of 1 minus the sine of 1. Since I know that 1 squared is 1, I'll just leave that out. So I'm going to type 2 cosine 1 minus sine 1. Remember, the graph said this is a small positive number, so I'm sort of holding my breath, hoping that this produces a small positive number and justifies my work. 0.239. I have to round. 0.239. That looks reasonable. I'm feeling pretty good about this, you should say. That looks like what I would have thought, a small positive number.
And that's 0.239 radians.
No, this is a ratio. This is rise over run. It's really a rise of 0.239. That's terrible. And a run of 1. In other words, that's the slope at that point. So because the 1 is the radians, and as soon as you take the cosine of it, then you're getting a ratio of adjacent to hypotenuse effectively. You're getting a rise over run here.
That makes sense.
That's a good question. Please interrupt regularly and ask those type of questions. It's a good question. So now I want to move on and see if I can find not just the slope, which is often, you're often done with the slope because we've done calculus now. If you're finding the equation of a line, that's really not a calculus problem anymore, but it's just really satisfying to go over there and look at the graph and say, not only is this the slope, but this is the equation of the tangent line that hits the curve right there. So I know the slope now is approximately 0.239, and I don't care on tests how you round. I'd be tempted to call this 0.24. I think I probably will. But I also need a point, and if I'm going to find the equation, I need a point. And I know that x is 1, and you remember from the graph over there, the y coordinate is 0.54. But of course, you could just do that yourself, right? because of course that would be found by going back to the original equation and finding out what happens when I put 1 in. Well, I have 1 squared times the cosine of 1, so 0.54. So now I have a point and a slope, and so now I'm free to kind of set up my equation. Maybe you've all been taught this different ways, but I kind of prefer the logical way. I know y equals the slope times x plus, and so I know the slope is, I'm going to just round it to 0.24. And I now know that in order for this to work, the y value we just said was 0.54 and the x value was 1. So I'm just plugging in all the stuff that I know. So 0.54 equals 0.24 times 1 plus b. If I subtract 0.24 from both sides, I get 0.3. So I get that b is 0.3. And so remember, that's just for one particular x and y. The reason I'm going back and replacing x and y with x and y is because I don't want just one point. I want all the points. And now that I replace the slope, which is constant, and the y-intercept, which is constant, then this is going to give me thousands of x's and y's, which create this tangent line. Now I'm just hoping that when I graph it, it actually looks right. Like that's the proof in the pudding here. 0.24x plus 0.3. If I go back to my graph, and maybe I'll get something wrong. Who cares? I'll fix it. It's like not a big deal. Y equals 0.24x plus 0.3. Oh, good. Looks right. Is it right? No, it's not. Why not?
You rounded.
I rounded. Of course it's not right. And that's why math books will typically not ask you to find the slope of this at angle 1. It'll say pi over 3 or one of the exact answers you have. So this is close, but it's not going to be perfect. But you didn't notice that, did you? When I first graphed this, it's like, is it right? Oh yeah, it's right. But just be aware, like that's the difference between things being perfect and things being approximate. But that's kind of cool. Again, what's neat about this from a physics perspective is, does it make sense in light of the project that you owe me on Monday? Like that could represent somebody standing at a point and looking at the top of a mountain. When you look at the top of a mountain, you are looking tangent to that mountain and your sight goes on past it. Or this could be a car traveling down a road. That tangent line would represent the direction the headlights are pointing, as I mentioned before. Or even better, that's the direction that your velocity is going at that point. So there's a whole bunch of physics about acceleration and velocity, and how your velocity, your car's speedometer might say you're going 50 miles an hour, and it basically means you're going 50 miles an hour in that tangent direction. But a second later, that's going to be pointing a different direction. Now your velocity is changing directions. It's still 54, but now it's pointed in a different direction. And so physics makes a big deal about all this. And these are just really cool applications for what you would do in a kind of a more advanced class, and why calculus is a prerequisite to some of those. So I don't need the teacher to grade this now. Does that make sense? Thanks to Desmos, I can say, I can write some little pompous note at the bottom that says, why don't you just use mine as the key, because I checked it and it's right. I hope you have a little pluck to you like that. That's cool. I love seeing those kind of notes on tests. You should not know, like you live in an age where you can check all this stuff. Cheat. And we didn't bother to cheat back here, but we probably should have, right? Even before I did all that math, wouldn't it have been a lot smarter to go in and say, what's f prime of 1? Obviously on a test, I'm going to be looking for evidence that you found this without cheating, but it's like, okay, good. Yeah, I must have taken the derivative right. I must have plugged the points in right, because the slope's supposed to be 0.3239, and that's exactly what I got. Good for me. Like, check your work. I want you to have access to this stuff, but obviously you're going to get almost no points if you give me an answer with no work, because I'm showing you how to cheat. But write me notes that say the right answer for the slope here is 0.24. So I'm going to continue finding the equation of the line using the slope of 2.24, even though when I did the calculus and got it wrong, I got 0.8 for the slope. So I'm going to continue with the right answer, but I don't know what I did wrong here. Like, that tells me you totally understand what's going on. Those are great notes to add to tests. Let's see. We have time for maybe one more. Let's do one more. You just need practice. That's all you need now. Let's see. We need to do a quotient rule problem. So let's make up something with quotient rule. And I wonder what would happen if it was like cosine of x over 1 plus the sine of x. And let's make it like 4. Let's take a quick look at the graph of that and see if it's cool. That's such a good memory. Cosine x, 4 plus the sine of x. So cosine of x is on top. Let's see if this is an interesting graph before we tackle it. Maybe it's not worth our trouble. Divided by 4 plus the sine of x. Turn those off. That's kind of fun. It's like a sine wave, except for it's elongated. And notice also does it look to you like it's not symmetrical there? Like, see how it's kind of like steeper on one side than the other? It's like a non-symmetrical sine wave or something. That's kind of fun. That's kind of a cool graph. All right, I can dig it. Let's do that one. So you go find, because we'll run out of time, can you use the quotient rule? Obviously, this is junk divided by junk. Can you use the quotient rule in your knowledge of sine and cosine to find the derivative of this? You don't, Vale. There's one rule yet you guys don't know. I have to be careful to make up problems that don't require it. Vale was asking about that. All right, I'm going to wade in. Let's see, quotient rule. Quotient rule, the top is the u, the bottom is the v. The quotient rule is u prime v minus uv prime. Same as product, but just with a minus sign. But then we have to divide by the bottom squared. So I'm just reminding myself what the quotient rule is. So the derivative of the top, which is negative sine, so there's u prime, times the bottom left alone. These parentheses are very important. All of that minus the top left alone, which is cosine. What's the derivative of the bottom? Could screw that up. What's the derivative of 4 plus the sine of x?
0 sine x.
0. We love plus signs. The derivative of 4 is 0, and the derivative of sine is
0
cosine.
cosine.
So, yeah. So the derivative of the bottom, the 4 doesn't even change anything. And then it's all divided by the bottom squared, which is not so good. I'm very not happy to see the plus sign because that's a lot of work up there. And so I'm just wondering, again, we're done. We're done. That's the derivative. You're done. Go home. But if I was to use it for something, we're going to run out of time maybe. So maybe we'll use some, maybe we'll use this, maybe we won't. But I don't know. Let's just see if this will go anywhere. Well, I have to distribute this minus sine. So that'd be minus 4 sine. And then minus sine times sine would be minus sine squared. And then that's a minus cosine squared. Ooh, I just got excited. Something good happens here. And then I don't know what to do on the bottom. Should I multiply the bottom out or not? I'm not really sure yet.
I would wait to multiply the bottom out.
Yeah. The reason I'm not sure I want to multiply the bottom out is because the only reason I would do it is if it was to cancel something on the top. But if I multiply it out, it's going to get bigger, which means if I have to plug in x as 2 radians or something, it's going to be longer to plug it in. So maybe it actually saves time. So I don't really want to multiply it out unless something cancels.
Isn't your top -1? Because it's -4 sine x, but doesn't the sine squared x and the cosine squared x equal -1?
Yeah, again, you got to be a little careful with that. But if you were to say minus, sort of factor a -1 out, wouldn't that be sine squared x plus cosine squared x? Again, that's a little hidden, like you got to be paying attention. And so, yeah, that actually goes to 1, which means it's -4 sine of x minus 1. So yeah, that's actually definitely progress. So I could say -4 sine of x just -1 over 4 plus sine of x squared. Now, if the top could be written as 4 plus the sine of x, then I could cancel a 4 plus the sine of x on top and 1 on the bottom, but I'm not going to get away with that. So I think I'm done. I think this is as far as I could go. But as far as I'm concerned in this class, don't stress out about that. It's like, write that on the test. I think this is as far as I can go. And if on the test I said simplify completely and you were wrong, that it does simplify a little further, then the question's worth 10 points and you lost 1. So what? Don't stress out about that. You're done with calculus on the first line. So I don't know, just for practice, because this might happen on the test, like let's pick a point to find the slope at, but let's do something that's going to come out exact. We have the time to do this. And I'm just thinking off the top of my head, let's see, there were pi over 3s and pi over 4s and pi over 6s. So let's go to this point. Let's find f prime at 5 pi over 6. I'm pretty sure that was one of the exact ones. I guess I better double check before I waste our time. 5 pi over 6, 5 pi over 6. There you are. Yeah, 150 degrees is 5 pi over 6. So the question is, can you get the exact slope? Can you get this exactly right? Because the angle this time I gave you is perfect. So what are you looking for on that unit circle? Since I'm asking you for the sign of that.
The y coordinate.
Sine is the y coordinate. I'm looking at it, seeing that the sine of y 5 pi over 6 is nicely, it wasn't the square root answer. I kind of got lucky. It's the 1/2 answer. So sine of 5 pi over 6 is a half. That's kind of cool. So that means this is going to be a nice slope. This is going to be not terrible, I think. So this is just a half. And of course, your calculator will tell you that. Don't forget, if you type sine of 5 pi over 6 in your calculator, it's going to say a half, and you're going to get lucky because as a decimal, you'll recognize that. So let's see, -4 times a half is -2 minus 1. On the bottom, we have 4 plus a half, but we have to square that. So that's -3 on the top. 4 plus a half is 8 halves plus 1/2, which is 9 halves. So I have 9 halves on the bottom, but it's squared. So that'd be -3 over 81 fourths, which is -3 times 4 over 81. So I think it's -12 over 81. And I do know that a 3 goes into both of those. So I could also say that -12 over 81. By the way, you should be cheating on your calculator. Do this on your calculator right now if you've never done this before. Sometimes you get these crazy fractions. Type -12 divided by 84. I'm sorry, 81. -12 divided by 81, and it gives you an unrecognizable decimal. Do you agree with that? Then right below the alpha button in your calculator, it says math. If you hit math, the very top one says convert it to a fraction. Notice it converts it back to a fraction for you, but it gives you the reduced version. Should you be capable of doing this by yourself without the calculator? Yeah, but what if the fraction was like 90,112 divided by 3,152 and you were supposed to reduce it because of my open math? You know, that's just kind of neat. It's a waste of your brain. You should be more than capable of doing that. But notice, this is not a decimal you would have recognized. When I looked at my calculator, I get 0.148148,148. I don't look at that and go, isn't that 4/27? Like, I don't recognize that like we recognized 0.6666 a while ago. And so if we did have to find the equation of the line tangent to the curve at this point, my open math is going to think we get this exactly right. So you can't say it's approximately equal to 0.148. and it is negative. You can't say that in my open math, right? It's going to want it to be perfect. So fine, you should be capable of doing it perfectly if it wants you to. Let's just check that on the graph and then we'll say we're done. So does that make sense? If I look at this graph and I go to the point 5 pi over 6, so I'm going to replace my x with 5 pi over 6, and I'm going to replace it here too, 5 pi divided by 6, because I just want to see where I'm on the graph. Stick that point on the graph. Okay, I am, turn it on. There we go. I'm there. There's where I am. And I look at that and I think, hey, that's a good sign. I do have a small negative slope there. So a slope like a -4/27 looks pretty darn reasonable. And of course, if I really want to cheat, again, though, notice the calculator is not going to tell you the answer to this 4/27. It can't do that. I have to look at the unit circle to kind of get this question exactly right. My advice to you is you have a book, and every odd question in the back of the book is there for you to check. Like, practice this as much as you need. If I give you, I err on the side of giving too few of homework questions because I don't believe in mindless practice. But there's a lot of you that your algebra skills are the problem here. And so if the 12 questions I assigned for 3.5 in my open math aren't enough, then go do 50 that you need to do, because you can do this. But you're, in a sense, if you're learning calculus on top of a lot of algebra that you should already know, then you got more to learn. But you can get this stuff. But my point is, we're right at a place in the class now where the wave is beginning to crest over the top of your head. And so if you're surfing on it, then great. This is an awesome day and you're surfing along and making progress and doing great. But it could also crash over the top of you. And it's about to be fun from now on or not fun from now on, depending on whether this is like feeling like too much to you now. Like, we've done a lot of stuff. We have 3 rules and we have all these trig expressions, and like that can feel like I'm underwater getting swirled around right now. You do something about it right now and practice a whole bunch more and stay after class and ask me a lot of questions. Don't just let this wave wash over you, because it's going to be fun. It's not going to be fun from now on, because we're going to be building on these ideas. Just like today, we worked on problems, but it built on, yeah, you practiced the quotient rule and you can actually use it. I'm assuming you know the quotient rule now. Well, did you practice enough that you actually do? So everybody's a little different. You might need more practice. Some people might need more practice to kind of go, okay, I totally get this now. Well, then do the odd questions in the back, or redo the problems in my open math. After the assignment's over, you can redo them just for practice. The only problem is they look about the same as they looked before. I'd recommend actually doing the problems in the back of the book. But you can make them up yourself. I mean, that's what I just did. I said, hey, let's find the derivative of cosine of x over 4 plus the sine of x. You can make these up. You can tell what the answer is using Desmos. Like, make them up, make them harder. But don't just sit there. Don't just do the 12 questions I assigned. I'm trying to cut you some slack. Anyway, all right. That's it. You owe me a project on Monday. You're going to be done with this assignment on Monday. We're going to go on and look at some applications on Monday. So you got 3 days. Make sure you come out of that awesome. Stay after class if you want to talk some more.
So I have a question.
Sure.
Before you were talking about on the quiz, it's going to ask us sometimes to completely simplify. Does that mean you want us to leave it in the form, for example, we use the one that does, say the answer was 1 over cosine squared x. Would you want that as 1 over cosine squared x, or would you want that as secant squared x?
I wouldn't care. Those are both simple enough that you're there. I'm never going to nitpick things like that. I'm never going to say I wanted it this way. Those are both simple. What I don't want is for it to be this big when it went to this big, and so that's hard for me to. Those are hard directions for me to give, and I don't want this to become really an algebra class. And so your question is good, but I'm never going to nitpick that.
Okay.
Nitpick. What else? What's bugging you?
I have a question about my open math.
Sure.
So, when I took a different math class during the summer, there was an option on my open math to message the instructor.
Mm-hmm.
And so it would give you like the actual picture of the problem so that like if you needed help on something, they could just message you back with what they could help you with. And I noticed that there's not an option on for your class. Is that on purpose?
Not really. Let me go look at that.
Okay.
Let's see. Can't remember where that setting is, but no, that's a good idea to have that on because I do want you to be able to either email me and say, hey, can we have a quick Zoom? We don't have to wait till class time all the time.
Okay. Yeah, because I was working on it last night and I couldn't find the button. I thought that maybe there was like a glitch or something.
Let me find that setting. These settings are always just really buried in here, and sometimes I can find them right off, sometimes I can't. Send teachers a message when students enroll. Keep going. Some of the rest of you questions. I'm going to find that and turn it on, Jaleesa.
I had a question. It's been bugging me ever since we first started class. Like when we tried to find the derivative of tangent, I got like almost there, but I didn't quite get there. And yeah, I'm looking at it, but I've been trying to listen to the lecture and look at it at the same time, and I wasn't getting.
Yeah. So tell me where you got.
So I got to sine x over cosine x plus tangent squared x.
Did you say tangent squared?
Yes.
And this was for, let's see. That was for the derivative of tangent?
Yeah, and I'm not sure, I might have made an algebra mistake in between the beginning and there, but I noticed that, the plus tangent squared x, that's half of secant squared x, so I'm like, I feel like I was on the right path, but I just might have missed something.
Let's go back and check it from the start. So the derivative of sine over cosine, according to the quotient rule, will be the derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom. Do you agree with that?
Yeah, I think I messed up when I set that up. I set it up as cosine x times sine x instead of cosine x times cosine x.
Yeah, you blew. I was thinking that doesn't look right. I think you blew it someplace. So this is the u prime. This is the v. This is the u. This is the v prime. I think you blew it somewhere in there.
You know, that makes sense because if you go down through what I did at a certain point, that cosine x over cosine x becomes 1. So it'd be 1 plus tangent squared x, which makes secant squared x.
Yeah.
I think I was just trying to hurry through it too fast because when we went out into the breakout rooms, I started trying to do it the completely wrong, like the wrong way of putting like tangent times x plus h. And then I was like, wait, this isn't making any sense with the hints he told us. And then when we came back out, I was like, oh, okay, I was doing that the wrong way.
Yeah, I want you to have enough time to hang yourself a little bit with these problems without leaving you there too long.
No, yeah, I appreciate that. I mean, I just, at least it wasn't, at least I'm not just completely not understanding what it was. It was a stupid mistake because I was trying to go too fast.
Nothing wrong with that. Keep going. Who else has got questions?
I had a question about the extra credit part on the project, and that was just getting the movable sun set up in Desmos. Is that something that you want us to figure out on our own, or do you have any hints?
You can ask me questions. Are you saying you looked at it and said, I don't even really know where to start? Is that true? Or are you part of the way in and you have a specific question?
No, I just have a question about, so I know how to get a point set up on Desmos where you can move it around. You have the A and then F of A, and you can move the point around.
Mm-hmm.
I'm just not sure how to like attach it to the line, if that's making any sense.
You're saying, we said this is now 10H, right?
Yeah.
And so you're talking about, you're talking about this point up here being able to move up and down, right?
Right. So did you want us to have the line, the sun rays actually attached to that point, or did you just want the point to move?
Yeah, the ray attached to it. In other words, when it's down here, then the line should look like this, in which case it actually hits up there. So yeah, in a sense, you have control with H to slide it around now, and that tangent line should stay tangent to the mountain, no matter where you slide it up and down.
Okay. Oh yeah, I see. You're not using like an A, F of A, because you don't want the X value to change. You're just keeping it at that same spot at 10 on the X axis.
Yeah, the X stays 10, but that allows the sun to kind of set to a different position. So in a sense, what you're saying is, hey, I figured it out at 1024. I'm sort of saying, could you refigure it out at say 1020, but then say, well, could I do this for 10 anything? Could I whatever I did with 24? I mean, really the method is to go back and say, whatever you just did with 24, stick an H there. And then in Desmos, you're going to have H be a slider, so you can actually set it to be anything you want. And you might start with just going into Desmos at some point and just saying something like H equals 24, and that's what makes a slider. So that should sort of make the answer to the problem. But the cool thing is now you can go back and change it to 20. You can say H equals 20. So the question is just really, can you do with H what you did with 24? So it's going to create a bigger, uglier formula. But the cool thing is Desmos can keep track of that, so that you don't have to do this 10 different times or redo it every time the sun sets down another foot. Now you got to redo it again, another foot, redo it again, now another foot, redo it again. Can you? And I will help you with that. Yeah, I mean, if the algebra that creates trying to do with H what you did with 24 creates a big mess, like there's something to be learned in that. So I'd rather you not take that on unless you take it all the way. And if I help you a couple of times and give you some hints or point out something you're doing wrong, then so much the better.
Okay. Yeah, I haven't tried putting in H for wherever I have a 24, but I'm sure I can start there, and if I get hung up, I'll send you an email or something between now and Monday.
Yeah. Yeah, please do.
Okay, thank you. Have a good weekend.
You too. Good questions.
Thank you.
Yeah. All right. We'll see y'all later. Have a good weekend.
You do this.
Thank you.